Hi everybody, welcome to my sixth video about axial bars. In this video, I'm going to talk about how we can deal with varying conditions on an axial member. And I'm also going to give an example of an axial bar that has a changing external force, and then I'm going to talk about how to find an internal force and a displacement. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. Alright, so talking about varying conditions. So basically when the area is changing, when the applied load is changing, when the Young's modulus is changing. Alright, so each of those is varying as some function of x. Alright, so when I learned this, I found it quite difficult. So I'm assuming that there's other people who find this piece difficult as well, so I'm going to try to explain it as clearly as I can. So when we had a discrete bar, alright, by discrete I mean each section that we had, we knew everything about it. So let's say we had a bar like this. Draw it up here. And this is section 1. Let's just say it had E1, alright, E1, and then this piece here had a different material, E2, had A1, A2, alright, it had, a load here, let's call this 2P1, alright, and why not, length 1, length 2. So for each separate section, we knew the properties, alright, the properties of this section did not change if you were here or here. The properties of this section didn't change when you were here or here. That's in contrast to another situation where everything would be changing. Alright, so for this one, in order to find an elongation, we use this formula. Alright, NL over EA. Alright, so the elongation of, let's say, this piece by itself would be the normal force in that piece, the length of that piece, times the E of that piece, and then the cross-sectional area of that piece. Alright, so now let's take a look at a bar where all of these things are changing. Okay, we'll analyze it. So let's just draw a theoretical bar here. Let's say it's tapering. So we have an area that's varying. So it's area as a function of x, where x is a coordinate, the running coordinate that starts at the base and goes out. Let's say also we have an applied load that's changing. So it might be a small load here, and then as we go along with x, it's increasing, alright? That applied load, we're going to give a symbol Q, alright, and it's varying with x, like the area. Now if we do a free body diagram and everything, we can find out that the internal normal force is also going to vary with a function of x. It only makes sense, right? External force varies with x, the internal force is going to vary with x. And just to make our life more complicated, let's say E is varying as a function of x. Alright? So it could be like only iron here, and then as you go this way, you could increasingly make it an alloy of like steel or whatever. Alright, so all of these things are changing as a function of x. Now how do we go about finding, well, first of all, internal normal forces, and then the elongation of this bar? Well, we're going to do it in the same way as we found it like this. Now you're probably wondering how are we going to do that, because everything is changing here, and here we had a section where everything was constant. Well, wait a minute, if we just use that idea, let's find a section where everything is constant. Now looking at this, nothing is constant. I mean, you can't take this piece and think it's constant. Well, what if we took a piece so small that all of these functions were approximately constant? Alright, let's just take a slice of this at a distance x away. Alright, we're going to have to make two cuts. Alright, let's take that segment out and draw a free body diagram of that. Alright, it's like this here, a small section. Now if you remember from any of your calculus classes, if you took a section small enough, a property that was varying over that whole piece would become exactly a fixed value if you took a section small enough. Alright, and that small enough section had to be a differential length, in our case dx. So the area you know, the applied load, the normal force, the E, are exactly constant from here to here if we take this so small. All right, so that's what we did, was take a tiny section dx, and in that section all the properties are going to be the same. All right, so in this tiny section it's going to be feeling a normal force. It has an area, it has an E, so it's going to be elongating. All right, now how much is it going to elongate by? Well, we'll get to that one second here. Let's just draw our imaginary elongation, d delta. All right, so what's the elongation of this piece? Well, we can do it the same way we found elongation of one of these pieces. If we have a piece where all the properties are the same, we just write this equation down for that piece. That's exactly what we're doing here. The elongation d delta for this piece is equal to the n at that piece. N at that piece would just be n as a function of x evaluated at a distance x away, times the length of that piece. Well, the length of this piece is dx, over the E of that piece. Well, that's just E as a function evaluated at that point. And then the same with area, the A at that point. There we go. That's all there is to it. The elongation of this tiny differential piece is equal to all the properties at that point. So now, just like we did before, if we wanted to find the total elongation of this piece, delta total, we had to sum up the elongations of each piece. So we added the elongation of piece 1 and the elongation of piece 2 together. All right, so we're discretely adding them up. You know, each one is like a value that we can add up. I'm going to do exactly the same here. We need to do a little bit different type of math because each piece is not really a discrete value. It's an infinitesimally small value. So to find the displacement of something relative to something else, we need to sum up all the displacements in between. And that's going to be an integral because each piece is so tiny. So we can integrate this to find the total displacement. From a distance, well, usually we find that we want to know it from the origin, but we could take it from any distance. We could find the elongation between here and here, any distance. So it's basically the limits of these could be anything, but usually we're going to say from x equals 0 out to a point. All right, so this is a very helpful equation. And it's very important to understand why this equation is true. So if you have to, rewatch the first part of this video. All right, so I have an example to quantify these ideas. I have a bar here. All right, just to make it easier, I'm going to say that E is the same and A is the same. In the next video, I'll talk about if they're not. And let's say we have an applied load. All right. And like I just said before, an applied load we give in terms of Q as a function of x. In our case, Q as a function of x is going to be a constant. We're going to call that Q naught. All right, so like 10 newtons per meter or 15 newtons per meter. All right. Now to find the internal force, we need to do the same thing as we did before. We need to make a cut. All right. So we can cut anywhere along this bar. We'll look this way. We'll make that cut at a distance x away from the base. All right, and we have a free body diagram of that. All right, let me quickly draw this out for you. Y positive x, just like that. Now we're going to have an internal reaction here and an applied bit here still. Q naught. So the sum of the forces in the x must equal to 0, just like we did on all the previous examples. All right, so negative n plus, well, this force here. How much force is in this applied bit? All right, so it's a force per area, or force per length, sorry. So this would be like newtons per meter. So we basically need to say Newton per meter times meter. Right, these go away and then you get the newtons. So we need to sum up the force per length times length. All right. Now in this case it's constant, so we could just say Q naught times this distance. But let's say it wasn't constant. Then you'd have to add up this piece as an integral. All right, so if it was changing, you would take a small section where the force per length is constant, and then you would like add them all up. So that's an integral. All right, so you'd say the integral of q as a function of x dx equals 0. So basically summing up all the forces here. All right, and we know q is a function of x. That's just a constant. All right, so that means n is going to equal to q naught, the integral of q naught dx from a distance x equals, well, we're starting here and we're going to here. We made the cut at distance x. So we're going from x equals x to x equals L. You can evaluate this integral, and equals to qx plus q naught L. All right, it's actually a function of x. Okay, so let's just go quickly plot that. I might as well plot q at the same time. Q is constant. And we say x equals 0, it's q naught L. When x equals L, it's 0. And it's linear because it's x to the power of 1. Twist the paper here to make my life easier drawing this angle. Alright, looks like that. Now, how are we going to find the elongation? Well, we're going to go back and use this formula that we just seen on the previous page. This right here. Alright, so d delta is equal to n as a function of x. That's just this here. Times the length, dx, over EA. Alright, now let's integrate this. The integral of d delta. And we want to know the elongation relative to the origins. We're going to say from x equals 0 up to a distance x. Alright, so let's just evaluate this side of the integral only and take a look at what that means. So it's going to be delta at a distance x minus delta at x equals 0. Well, we know that there's never going to be any motion when this thing is fixed here. So this here, this term is always 0. So you can just think of it as the integral of this side of the equation is just delta. Alright, delta equals. Now, how to integrate this side? Going from x equals 0 to x equals x. So really that's just an indefinite integral. Alright, e and a are constant regardless of what x is. That means we can take it out. If you remember your rules of calculus, 1 over EA. We integrate this, becomes q naught Lx minus q naught x squared by 2. Alright, now if you want to find the total elongation, so how much the bar has moved at the very end, we want to figure out how much this point has moved. We simply evaluate this equation here at x equals L. Alright, so delta, let's just write this first. Delta as a function of x, it's 1 over EA times q naught Lx minus q naught x squared by 2. Alright, now if we want to find what the elongation is at the end, like I just said, we evaluate this from x equals 0 to x equals L. X equals 0, this is all 0. X equals L, you plug in your L's there. Your delta total turns out to be q naught L squared over 2EA. Alright, now let's plot this elongation. Alright, and you see here it's a quadratic with a value of this at the very end. It'll look like this. Alright? And that's exactly how we find this elongation. You integrate all the variables. Now check it out, something really interesting. The applied load is constant, this is linear, and this is quadratic. So every time we're raising the power of x one more time. Okay? Just a quick review. We use the same principles on a small bar as a big bar. We approximate the values over a really small distance as being constant. And we develop the same elongation equation as we did for a discrete bar. This example, that's exactly what we went through. We realized every time you basically go in one order higher. Alright, thanks so much for watching, guys. I hope this helped. And I'll see you in my next axial bar video.